For those who don't know me, I am Pedro dal Castel, and it happens that I am also Pedro dal Castel for those who know me. In this lecture, we'll cover the second part of chemical fields, which is secretion and absorption, especially focusing on model building exercises. So I will remind you that this is being live streamed, recorded, and will be distributed on YouTube, and several links here for you to access our materials. And I just uploaded the new slides to the student material folders, so you can get the exercises ready to go and also the slides. Okay, so the objectives here are to learn how to implement secretion and uptake in CompuCell3D, and implement what you learned about modeling with James yesterday on two model building exercises. And the topics will be source, link, sink, secretion, excretion, secretion boundary conditions, secretion and uptake specification in CompuCell3D, and the model building exercise. Because I already went through most of source and sink, I will just review, but there is a motivation before I start, which is here we are connecting the dots with signaling, because again, cells can only sense the immediate surroundings, which means the system is local. So the cells just know about what is going on inside them and the immediate surroundings. So how can one cell know what's going on elsewhere? It has to receive a signal. And these signals are created, transmitted, and received according to the rules we're going to establish here. So we already explored diffusion, which is a transmission process. And here we will go over creation and receiving the signal and destruction of the signal in the form of secretion and uptake. This will be crucial for building the two models. The first one is an ecosystem where bacteria A consumes a nutrient, generates waste, which another bacteria consumes. And the avascular tumor spheroid, where cells consume nutrients, grow and divide, and if they are not receiving enough nutrients, they die. So again, secretion source is modeled by a constant rate to the diffusion equation. A sink is the same thing, but it's a negative. Watch out that if you just do negative secretion, your field can be negative, which is not desired. If you have secretion and decay, your field tends to reach a steady state constant value, and the relaxation time is 1 over gamma, gamma being the decay coefficient. We went over secretion, excretion, and exocytosis. Again, secretion is release of useful signals, excretion is waste, and exocytosis is a biological mechanism that the cells use to secretion. In CompuCell3D, you specify secretion first with by defining a rate, which can be a constant rate or constant value. The boundary conditions, which are secretion on all cell pixels, on just the center of mass pixel, or the boundary. And you can also set conditional secretion, where the cells only secrete a substance when they are on contact with another cell type, or any other condition that you want to set in Python, because you have a lot of flexibility there. Now let's take a closer look here how it would look like if you set a constant rate of secretion. So here in the left case, we have the constant secretion rate. So every Monte Carlo step, the cell adds a constant value to the field. And this is the field profile we would see growing and growing every Monte Carlo step. So you can see, I mean, you cannot see this growing in time, but if you let this run, you see that the field is always increasing to infinite, to to infinity. If you're using constant concentration instead, then the cell will hold the field value at a constant value, in this case 10, which means if you let time go on, the entire space will eventually be at concentration 10 and not just increasing forever as in the constant rate of secretion. To include secretion to your simulation, there are two ways. The first one, similarly to including diffusive fields, you can set that to in the wizard, and you can also set that in the XML. So you go to the XML, into edit, there is a CC3D ML menu with the plugins menu. And then you find secretion, you click there, and it's going to include a secretion plugin to your XML file. In Python, which is what we are going to focus on today, you can do the same. To edit offers code snippets of secretion manipulation in Python. So you just go to CC3D Python, secretion and uptake, and then there are many options, like all these options you are seeing here, of where secretion is taking place, constant secretion rate or constant value. You can select all these options on Python. And the advantage of doing all of that in Python is that it increases flexibility, where you can specify like conditionals, hill functions, everything. We are going to use only Python specification. And if you want to know more about setting up secretion, you can check the documentation. I hope this link works. Yes, it does. So you'll find all the information useful there. Also, oftentimes you want to access metrics of your field. For example, the total field integral, the total amount of field in the simulation. You can do that by getting the secretor object and then calling the method total field integral. It will return the total field amount in all the space. There is a method called amount seen by cell. This is similar to the field integral, but only at the region where the cell is. So only the concentration seen by the cell you're giving. So you have to give what is the cell you want to measure the total field, the field integral at, and then it returns the amount seen by that cell. There is also a total count method. So if you call this secrete inside cell total count, it will secrete, it will tell the cell to secrete substance, but it will keep track of how much the cell has secreted. And by the way, I use all like these three in my model of viral infection because I need to measure things, for example, total cytokine level. I need to know how much a single cell is sensing of a cytokine. And I also need, for example, to keep track of how many viruses a cell has released. So these three, although we are not going to use them today, they can be critical for a serious modeling project. Now going to uptake. Uptake is the opposite of secretion. So instead of the cell releasing something, it is eating something up, bringing something from the external medium to the inside of the cell, usually via vesicle mediated transport, which we call endocytosis. When a cell is endocytosing, we consider the cell as a sink. So instead of a source, it is depleting the material of the field. But again, if you just set it as a sink, the cell would be consuming, and eventually your field would be negative. And that doesn't make sense when we're talking about concentration fields. So the update we're going to implement has to be proportional to the local field concentration. Another important consideration is that if you provide like too much of that material to the cell, there is also a maximum rate the cell can absorb that material, uh, because it is limited. I mean, there are only so many vesicles the cell can produce, and it's not going to. If you give 1 kilogram of sugar to a cell, it's not going to take 1 kilogram of sugar in a second. So our uptake function is saturating. So there is a maximum uptake rate, and it's also, and before a threshold value, it is proportional to the field concentration. And we write it like this. This is a piecewise function. So our uptake rate, if the concentration is below the saturating concentration, it takes the form of a decay term, so minus gamma c. And if the concentration of the field is above a saturating concentration, then it takes the form of a sink. Uptake comes with the secretion plugin. Oh yeah. So if you already have the secretion plugin from the wizard or from the XML snippet, you can use uptake already. You don't, there is, it's not separated. The secretion plugin envelops both secretion and uptake. And uptake can only be set in Python steppables. It cannot be set in the XML. So that's another reason to to specify everything in Python. Quick note, uptake is negative because it's from the reference of the field. So if the field is losing material to the cell, when you track the uptake inside cell total count, it will give you a negative value. That's often non-intuitive, like you want to know, oh, how much material has this cell taken up, and the simulation will inform you minus 10, and then you, what the hell? What is going on? Why is this minus 10? Well, because it's from the reference of the field. The field lost minus 10. So if you are going to set thresholds, for example, the cell will grow if it has taken up 10 units of a material, then you have to invert the sign. Then you have to do minus secrete or uptake inside cell total count, total amount. Sorry, this thought variable here. You have to invert the sign of this guy here to get a positive number. Yes, so sink is a constant decrease of the field, and decay is a decrease that is proportional to the field. So this CDT equals minus S. This is a sink. This CDT equals minus gamma C. This is a decay. It depends on if it's proportional to the field concentration or not. Now, first exercise. Here, to consolidate and practice implementing secretion and uptake, we're going to build this very simple demonstration, this exercise number 0, which is one cell secretes a field and the other cell absorbs. So the result is what you are seeing here on the video. This is what we are going to achieve by following the steps in the next slide. So here we are all grown-up adults, and by this point, I think we can follow these steps without too much step-by-step detail. So I will leave these steps on screen, and I'll give you 5 minutes to work on them. And as you face challenges, type on chat, and I will help you out. After these 5 minutes, I will catch up and do follow the steps myself to build the demonstration. And just as a heads up, from now onwards, we'll basically do exercises like this. We'll give you the instructions and you will do the model specification yourself. What would be the chemical field here? Do you mean the name of the field? You can choose any name for your field. In the slide that says sink when concentration is high and decay when concentration is low. Can you explain in biological terms what that means? So explaining in biological terms what that means is the cell can the uptake rate of the cell is limited. The cell cannot take up an infinite amount of material per Monte Carlo step, per unit of time. That's what it means biologically. So it is proportional to the concentration of the field up to a certain point. Above that point, the cell cannot take much more than that. Is the cell making a decision here about sink versus decay? Not really. You could argue that the cell is making a decision, but you don't need to understand as decision making. There is no like pathway controlling a decision like that. You can just argue that it's a logistical limitation of the cell machinery, right? I'm a little confused on the difference. Okay. If uptake is negative, is secretion positive? Correct. It is. Secretion is positive. Uptake is also positive on the parameters here, but it will decrease the field material. Yeah, you can also manually add, as Anastasia is pointing out, you can do this. So there are two ways of implementing your secretion plugin. You can check it on the wizard on cell properties and behaviors. You can also go on to edit. There is a CC3D ML drop-down menu, plugins, and then secretion. What the boundary conditions? You can so you can choose the boundary conditions that you think are appropriate. For achieving this pattern here, I think that the appropriate boundary condition is constant derivative equals 0. And I did not talk about the boundary conditions because I want you guys to think about it. Good question though. Secretion type. Well, here I'm using secrete inside cell. This is on Python, right? Where does this go, by the way? I'm showing you this chunk of code. Where is this going in the code, in the steppables? Exactly where? In the step. Great. Okay. I see you have understood the structure of the code. I'm confused. How to place the two cells separately using the XML? Oh, yeah. So there is a box initializer thing in the XML. You can create two of those. You can you can create two chunks of that code separately. I will show you how to do that. And then you have two boxes, two box initializers. And then you can set one cell. Okay, why don't I do that? So I will go over the steps here. And if you got stuck somewhere, you can stop what you're doing and look at uh, my screen share. Okay, this is the exercise. Now open my to edit. Okay, so here I will go CC3D project, new CC3D project, next. I will reduce the lattice dimension just so that it runs a little bit faster, but that's not required. Rectangular slab is fine. Next. Then here I need two cell types, so I'll do cell 1 and cell 2. Then next. Here in chemical fields, I will just type like I don't know, some field. Next. Now here I have my cell properties and behaviors, but I will not check secretion just to show you what you will do if you don't have the secretion box here. So I will just go next. Oh, let me just get like volume flex. Next, finish. Because I want to freeze the cells, right? If I want to freeze the cells, I need a volume plugin. So right here, I have volume. Because I want the cells frozen, I'm going to increase the lambda volume to something like 200. Okay. So what I just did is I came over here and increased my lambda volume to 200. Now I am going to fix my diffusion solver. So first I'm going to set like a larger diffusion coefficient. And also I'll set like a global decays of 0. And diffusion coefficient in the cells doesn't really matter. The decay coefficient I will set to 0. You can have some decay, it's not a problem. So now here in my CC3D version, I have secretion on the diffusion solver. I don't want this, so I can like completely delete this chunk or set these values to 0. I will set these values to 0. And here I would like to have a constant derivative 0 on all boundary conditions. So what I'm going to do here is I will set constant derivative here on y to 0, and then I will just copy these two lines and paste them on x. So now I have constant derivative equals 0 in all boundaries. Is that okay so far? If that's okay so far, I will go to including the secretion plugin when you do not have your secretion plugin here. So I'm going to CC3DML and the plugins and then finding secretion here. Can you go slower? I don't have the same code because of 4.7. Okay. So here on, I'll repeat the diffusion solver part. So here I just increased the global diffusion constant. I set decay to 0. I set secretion to 0. I think you do not have this line. It's okay. You just don't do anything. And then I did constant derivative equals 0 on all boundaries. Let me know when you have all these good to go. I also set my lambda volume to 200 so that the cells are frozen. And again, here on diffusion solver FE, I increased my diffusion constant a bit. I set zero decay constant, zero decay coefficient for cell 1, cell 2. I have two cell types. This is important. Two cell types. Then I have zero secretion. If you don't have the secretion um, data, you don't need to care about it. Okay. Rodrigo is getting the result right, which is fantastic. Then here I set constant derivative to 0 on all boundaries. Can I go to including the secretion plugin now? Okay. So I open the space here. Make sure you are not inside a code box or a code block. So here I go to CC3D ML plugins and then secretion. Copy. So find an empty space, CC3D ML, plugins, secretion. Yeah, Rocio uh, probably has a XML syntax error. Can someone take a look at that? Okay, so I went to CC3D ML, plugins, surface, sorry, secretion, and now I have a secretion plugin here. Okay, now with this secretion, I want to leave this empty like this. I want to have just the plugin secretion in there. Is that clear for those who don't have secretion yet? So I added the secretion plugin and I leave it empty. Make sure you have the correct syntax. There should be like brackets here, bracket slash plugin. Okay, all good? Okay, all right. So if you have that, then you want to create two cells. To create two cells, you come here to your uniform initializer, and there is this region block. What you want to do is copy and paste this so you have two separate regions like this. And now here, with these two separate regions, note that I just copied and pasted this code block here. I just copied and pasted. You want cell 1 in one place and then cell 2 in the other, like this. See cell 1 in one region and cell 2 in the other region. Now here, what you want to do is to set a position of your cell. For example, from 20 to 30 and then like 70 to 80, the other one. And then the Y has to be the same for both, something like 45 to 55, 45 to 55, so that they are on the same X line, same Y height, 10 pixels width, so you make sure you're creating only one cell. And if I run this just to show you how this looks like after these changes. This is how they look like. So they look a bit ugly, but that doesn't really matter. And of course, I still don't have a field. Like everything is blue because it didn't set the secretions and uptake. But this is how the cells look like. Okay. So I initialized them the same distance to the center in two different regions and same Y height. Let me see if you, so this is all for XML. So what did I do in the XML? I set high lambda volume. I set higher diffusion coefficient. I set zero decay. I set zero secretion. And I set constant derivative equals zero for all boundaries. And finally, I created two cell regions. The first region being cell 1, the second is cell 2. And I set the X and Y minimum and maximum regions to be on the same Y height and equidistant X position from the center. Do we have to have the secretion plugin in the XML even if we are adding a steppable in the Python file? Yes. Yes, we do. Yeah, so that's the other thing I did. I included a secretion plugin, and I did so by going to the CC3DML, plugins, secretion. Okay. I will assume that everybody is going well here. So the final thing I need to do so that my simulation works as intended is here I write that code that says cell list by type self.cell1. And here the slide is showing cell A and cell B, but my cell type names are cell 1 and cell 2. So I have to use the name cell 1 and cell 2. All uppercase letters, otherwise it doesn't work. Now here I have to include the secretion for cell 1. And I will do that by coming to the CC3D Python drop-down menu and then chemical no secretion uptake right here. So here I have all the options. So I have amount seen by cell, secrete inside, total amount, uptake. And here, as the slide indicates, I'm going with secrete inside cell. And here it's giving me a bunch of syntax. The first line is getting the field object. Let me sure I'm indenting this correctly. Here, the field name has to be the same as the name of the field on the slide, on the XML. So the name of my field is some field. So it has to be the same here, some field. Now I can delete these comment lines. They are not doing anything. And I'm going to set a secretion of 0.1 as in the slide. Can you show where your secretion code block is? In the XML? Yes. My secretion is here. It doesn't matter where it is as long as it is not inside a code block. Okay, now coming back here, I set the secretion. Now I need to set an uptake for the other cell type. And I will do so by just copying this whole chunk here. So it has basically the same structure. The difference here is that now I have to do a for cell in cell list by type cell 2. Now I'm getting the cell 2. Is it normal that my class is called differently? Yes, it is normal. Depends on how you named your simulation project. So, but here I don't want a secretion, I want an uptake. So I'm coming back to CC3D Python, secretion uptake, and then I will do uptake inside cell. I already took the field secretor object, so I don't need this line over here. It's already here, getting the secretor. So I don't need that. So I'll delete all these lines. and this one too. And now I'm going to set the values on the slide. So 10 here, 0.1 here. And if now I think it's all good. So I will open the simulation. And if I change here to my field visualization, this is what we see. The field is slowly being produced by the cell on the left. And you can see this shade produced by the cell on the right. And how the concentration, how the gradient is created, right? The gradient here is pointing to the left or to the right? Where is the gradient pointing to? Like here where my mouse is. Here in the middle, where is the gradient pointing at? Left, correct. Is it normal that my class is yes? Can you show once again how you insert secretion? Do you mean inserting secretion on the XML or Python? Has this 0.1 to match the one in XML? No. No. The one in XML is only for the initial setting? No. So you should not have secretion settings on the XML, I mean the parameters. Like look at my secretion plugin here. My secretion plugin is empty. So this is all as Michael is saying, this only loads the plugin. It's not setting the the parameters. Okay, so the Panjan asks, how am I getting the secretion code in Python? Let me pause the simulation because my computer is freaking out. I come here to the CC3D Python. Here is where all the code snippets are. So if you want to visit cells, you come here, visit all cells, so on and so forth. So to get the secretion uptake syntax, I come here, secretion uptake, and then I choose one of those. I missed that to fix one bug. Yeah, I hope that this is the answer to your question. Secrete inside cell over here. Yeah. Then if I do this, I get all these lines here. You see, there is a line which is secretor equals get field secretor. You do that to get the field object. It has to have the same name of your field. So look, I have some field here as input. This name has to be the same name as the field name in the diffusion solver FE you have here on the XML. So the name of my field is some field, then the name here is some field. Then I have a for loop here on all cells of type cell1, and then I do a secretion inside cell with these parameters. And then I have another for loop over cells of type cell2, and I do I do uptake inside cell with these parameters over here. The name of the cell type has to be capitalized, yes. So if you take a look here, my XML, I have cell 1 and cell 2, it's lowercase letters, but right here, when I do a cell list by type, I do self dot cell 1 uppercase, cell 2 uppercase. And that concludes the exercise. I will launch the poll. Let's see how you guys are doing. This code is in the student materials. So if you are completely clueless why your simulation is crashing over and over again, you can just download the simulation code. Maria is asking, is this okay? What do you think, Maria? Is this okay? Is this representing the concept that we are exploring here, which is one cell secreting a signal and the other cell receiving it? Is it okay that your cells are moving? Is like is your simulation corresponding to the idea of one cell secreting a substance and the other cell consuming it? Did you add the for loops or was it automatic when you added the Python snippets? You can also use Python snippets to add the for loops. So you can come here, CC3D project, visit, and then all cells of a given type. This gives you the for loop right here for cells in self dot cell list by type. And it even suggests you that you can do multiple types at once, which is very interesting. But no, I just typed it. That's what I did. I just typed it. Inside cell is all the pixels of the cell secrete. Okay, let me see how the completion poll is going. Oh, and I'm still using the wrong exercise completion poll. Let me launch. Oh,
Just leave that one for now.
okay. Let me end this one. Okay, do I proceed or do I launch another poll?
Looks like people might need just a couple minutes. I would say wait 2 or 3 more minutes and then go ahead.
Okay. I'll launch the poll again then. May I ask if the white line is the field? So if there are white lines moving around as you visualize your field, you probably checked on tools, configuration, field visualization, the ISO lines. The ISO lines are lines where the field has the same intensity. Yes, it is related to the field, and it's just a visualization tool. Not sure why, but my simulation stays like this regardless of how long I let it. Oh, bro, what did you do? I think I know what you're doing. I think your diffusion is 0 on medium, in medium. The poll is incomplete, yes, because I launched the poll that doesn't have the writing part. Many people need more time, so I will wait a couple more minutes. And Allison, you probably set diffusion 0 outside cells. I think that's why. Diffusion, yeah, diffusion 0.
For the poll, For question 3, do you see untitled question and choice 1, choice 2? That's what I'm seeing.
Yeah, this is the most important question, so choose carefully. Pedro, the correct one is just, it's called exercise completion poll. It's one question for next time.
Okay, so this is the wrong one then.
Oh, okay. Okay. For the secretor secreting side cell line, I get an error if I put 3 arguments. Of course, because secretion only takes 2 arguments. You should do cell, comma, 0.1. So the error is correct. Is there a way to better contrast the absorption? Oh, Mika, I mean, yeah, you can increase uptake rate, for example. It's not critical. I mean, what you got is right. Okay. Okay, I will give you 15 more seconds. All right, let's move on. Um, what is this? Let me close this. Come back to the presentation. So let's keep going. So we'll do a modeling exercise. And this modeling exercise is what you saw in the beginning. This ecosystem with two bacteria. Uh, so one bacteria take up the nutrient, generates waste, and the waste is taken up by bacteria B. And we'll do that by thinking about what we learn with James. About modeling. So what is a model? If you search like in Google, you get imitation, which is good. Generally, I define model as a representation, and it is a very general purpose definition. That's why I like it. And there is ChatGPT definition. A model is a simplified representation or abstraction of a system, concept, or phenomenon, often used to explain, predict, analyze its behavior. Models can be physical, mathematical, conceptual, or created to simulate real-world processes, facilitate understanding, provide a framework for testing hypotheses or making decisions. Uh, and this encompasses all the things we call model. So even like this model here of a building, you can call that a model. And even simple things like addition, you can understand that as a model too. So you are abstracting the idea of joining things together and increasing their numbers. And in James's modeling framework, we have objects, behaviors, interactions, dynamics, events, and initial and boundary conditions. So for objects, we have, for example, medium, cells, fields, networks. For behaviors, we have growth, death, migration, diffusion. For interactions, we have repulsion, adhesion, signaling. For dynamics and events, We have, for example, the isotropic diffusion equation. We have linear growth. We have symmetric division. For initial and boundary conditions, we can set, for example, the position of the cells. And for boundary conditions, we can set no flux, periodic, so on and so forth. So for the exercise we just done, we could organize these concepts as we have medium, we have cell A, cell B, and field as objects, and we have the following interactions. So cell A secretes a field, and cell B absorbs a field. Notice that cell A and cell B do not interact. They do not interact here. We're not specifying interaction between cell A and B. This is critical because cell A communicates with cell B, but they are not interacting. Interactions are local. Actually, what happens is that cell A interacts with the field and cell B interacts with the field. So they communicate through the field. You could say that maybe it's an indirect interaction. I couldn't get mine to work. Hayden, can you provide a link to the code? Then behaviors, so our cells don't move. Maybe they move. So I saw someone building a simulation like that where the cells would move around. Then the cell could diffuse. But the field here has a behavior. The field diffuses. Again, behavior just takes one object to take place. So the field alone diffuses. And we have dynamics. So for example, isotropic diffusion equation for the diffusion of the field, constant rate of secretion, and relative absorption with saturation for uptake. Now I want you to do the same for this conceptual model. So I am presenting you a conceptual model here on the right side. So in this schematic, I have medium producing nutrient getting consumed by bacteria A generating waste, and waste being consumed by bacteria B. And the idea here is that these bacteria are trying to survive. So if they are not getting access to their nutrient, they cannot proliferate. If they don't have access to their food, they can't proliferate. So build a model structure for this conceptual model. What are the objects? What are the behaviors? And what are the interactions? You can also set initial condition and boundary condition and dynamics, but the main ones for now is objects, behaviors, and interactions. So I will give you 5 minutes to type that down. Something like this. Objects, object 1, behavior, object 1 does this, interaction, object 1 does this with another object. I see only 3 answers, 4 now. Martin, medium bacteria 1, bacteria 2, nutrient field, waste field. Bacteria grow, bacteria die, bacteria divide. Okay. Interaction. Medium replenishes nutrient. Bacteria 1 consume nutrient. Bacteria 2 secrete waste. Bacteria 2 consume waste. Okay. It's good. Wing. Eh? Kaya. Bacteria A grows, divides, and dies. Interacts with bacteria B through excretion of waste. Waste and nutrient fields. Eh? Rossio. Medium bacteria A, bacteria B, field 1, field 2. Bacteria A absorbs field 1 nutrient. Secretes, absorbs. Medium bacteria, nutrient, waste. Interaction. Secrete, absorbs, secretes, absorbs. Grow, die, divide, diffuse, diffuse. Okay. Bad A. Nutrient. Okay. So I gave my feedback. And this is what I did. So this is my answer. I have medium bacteria A, bacteria B, nutrient, and waste. It is important that you have medium, okay? Medium is an object because medium is doing something. Medium is interacting with something. So medium is an object. Otherwise, your model structure is not reproducible because there are other methods that are not called CompuCell3D, and believe me, there are many. And they do not have explicit medium as we do. Interactions. Medium replenishes nutrient. Bacteria A consumes, releases waste. Bacteria B consumes, zero surface tension between all cells. Ugh. Behavior, cell grow and divide, cell die, and waste and nutrient diffuse and decay. Good. Any questions here? If a cell secretes extracellular matrix protein, would the secreted DCM be considered medium? Would be depends on how you implement it. You could consider that a field if it diffuses, or you can consider that another cell type. Neutral contact, yes, neutral contact. This is not something you need to state. So far, so good. Now we build pseudocode. Now we need to implement this in CompuCell3D, but it takes a lot of time to actually build a code. So we are going to build pseudocode instead. What is a pseudocode? What is pseudocode? I learned yesterday that there is no article before pseudocode. So what is pseudocode? Pseudocode is a simplified, arbitrary, spoken language for designing algorithm. So it's something like, you do a loop over cells. Now, if the cell is of type cell does this. If this happens to the cell, then this. This is a pseudocode. This is pseudocode. Here is pseudocode example. Pick a number A. Start process. User enters number B. If B equals A, break process. If B and A are different, say, you are wrong, try again, and repeat process. Otherwise, say, congratulations, you won the game. So if B equals A, breaks process, which means you get out of the process and say, congratulations, you won the game. So this is a game for guessing the number. It's a flow chart, yeah, more or less. A flow chart would be a good form of pseudocode presentation. Isn't that taking way more time than just implementing it using code snippets? Clara, no, for two reasons. First, we don't have time to implement the code anyways. The code implementation takes longer than 30 minutes. We don't have 30 minutes. So by design, we are not going to do the implementation in CompuCell on this session. And the second reason is, when you are writing a paper, oftentimes you present the pseudocode and not the code. The code, you leave a link to your GitHub page where the people can download and run things. But what you do is present pseudocode to the audience, the reader, because the pseudocode is replicable. In other words, if I give you pseudocode, you can implement that on CompuCell3D. Hayden can implement that on Physicell. Alan can implement that on finite elemental models. If I give you a CompuCell3D code and you want to implement that on another framework, you have to do what? The pseudocode. So the pseudocode is oftentimes more relevant scientifically than the code itself. I reassure you, we are going to build a lot of simulations during this workshop, so there is no shortage of code writing. And in the next session, we are going to do precisely that, lots of coding for the avascular tumor. Mark just gave an answer. Medium secretes filed. No, medium secretes filed. Nutrient. Bacteria A uptakes field nutrient. Bacteria A grows and divides if necessary. A secretes feelings. Yeah, it turns out that to make it something you can implement as a code, it has to be a little bit more sophisticated than that. Initialize X bacteria cells, Y bacteria B cells. Initialize field, initialize diffusion. Each Monte Carlo step, loop over all bacteria. If energy is 0, kill cell. Oh, that's a good, interesting idea. So here she is tracking the energy of a cell. And if the energy reaches 0, the cell dies. And if the energy is non-zero and the energy is not at capacity, the bacteria will uptake nutrient, update energy, release waste, and if bacteria is if there is energy, the cell grows and decrease energy. Oh, this is very sophisticated so far. If bacteria volume is twice the target, then divide cell. Split volume and energy equally. This is very carefully thought out, so I like this a lot so far. Because that's almost exactly what I need to implement so that the code works. If bacteria B energy is different than 0 and bacteria B energy is not at capacity, uptake field, update energy. If energy is non-zero, grow. Decrease energy when grow. If volume is twice, divide. Split volume and energy. Good. But I'm wondering practically, how can I translate field, uptake, secretion with an energy term? I am having trouble to figure that out. Well, you can assume that every certain amount of nutrient consumed, there is an equivalent amount of energy acquired. So you can relate them one to one. So for every unit of nutrient I take up, I increase my energy by one. And it means that the cells can accumulate energy. And so they can survive longer if they lose access to nutrient. And in CompuCell, you can do that using cell dictionaries. So you have an entry of the cell dictionary saying energy, and then um, you keep track of the amount taken up by the cell and add that value to your energy entry of the dictionary. Start process. If medium produce nutrient, bacteria A eats nutrient. Oh, this is interesting because Alma, you are conditioning bacteria eating nutrient to medium producing nutrient. But if a medium produced nutrient in the past and it's not producing nutrient anymore, but there is nutrient available, bacteria still can consume it, right? You don't eat a bread because you have 10 minutes left. Okay, let's go on. This is possible pseudocode. So here I'm doing more or less what Anastasia suggested. So medium produces nutrient and then I loop over all cells. And then I test if cell has no energy left. If that's true, I kill the cell. Then I test if cell type is A, is one of the cell types. Then I test if the cell is not full of energy. If it's not full of energy, I take up nutrient and increment cell energy. And then I release waste. And then I test if cell has energy. If cell has energy, I grow the cell and decrease energy. I decrease energy no matter what, actually, even if the cell is not growing because there is a basal metabolism rate. Then I test if the cell is type B. If the cell is B, I test if it's not at capacity. If it's not at capacity, take up waste as food, and then I increment cell energy. Then I test if the cell has energy. If true, grow cell. And then I decrease energy. If the cell size is double the original, I divide the cell. So this is almost exactly what Anastasia suggested, which is very good. Very good. The exercise is accessible to you in the Drive folder. So you can come here to this link and day 3, or I see it already here, but if it gets lost, it's called Ecosystem Exercise Secretion Uptake. And you can download that and run. And it looks like this. And what's most interesting about this exercise is that it kind of reproduces a spatial pattern that we are very familiar with. And that's only possible because we are doing spatial agent-based models. And what is the spatial organization that we are looking at here, that we are very familiar with? What is it? What is going on with these cells? They are sorting, exactly. Why? Why are they sorting? What is the key mechanism that make them sort? I still haven't got a satisfactory answer yet. No. The fields are not equal everywhere. Ritesh, Ritesh, and who is the other one? Ripla. There is addition is neutral here. There's no addition going on. Addition is neutral. Another one saying the same thing. Surface tension assumption. No, there is no surface tension BS here. Depletion of nutrient field. Okay, that's more or less. Turing patterns of fields promote growth of different bacteria in spatially distinct areas. Oh, look, Anastasia is on the way there. On the way. Energy balance. Bacteria 1 likes me. Oh, yes. Why, Rodrigo? Why is that? I'm still giving you the monocle face. Unless you explain why bacteria 1 likes medium and the other one likes 1. I see that we are struggling here. Okay. That's still not enough, Rodrigo. What happens when bacteria 1 is not close to medium? And what happens when bacteria 2 is not close to bacteria 1? That's key. It doesn't actively move around 1, Rodrigo. You're missing the point. When bacteria A is near the medium, it grows, and when away from the medium, it dies. Okay, Troy is on the right track. I'll give you a thumbs up. They die. Okay, okay, okay. The highest concentration of nutrients will be in the medium. So bacteria A prefers to be as close to medium as possible. Okay, that's good. That's good. I think that's our answer right here. It dies off and not get enough nutrient to grow. Diffusion distance. Diffusion distance is relevant, very relevant here. It doesn't move around, but it can only survive around. Correct. That's correct. So there is a survivorship bias. I don't know if that's the correct term here, but the only uh, viable bacteria A are the ones making contact with medium. And the only viable bacteria B are the ones making contact with bacteria A because of the signal being produced by medium and being received by cell A, and the signal being created by cell A being received by cell B. This is what ultimately produces the spatial pattern we are observing here. It's not adhesion. And for those who miss hardcore coding, next session we'll have more on that. We'll have actually hardcore coding. And you can actually download this simulation here that I'm showing. I'm showing just the results. You can download that. The link is somewhere in the chat. And run it by yourself. You can also, as a homework, try to implement it yourself. Because there is the pseudocode here, and we are all grown-up adults, so we can start doing it. In the next session, we'll go over the avascular tumor. The avascular tumor has a necrotic core where the cells are too distant from the source of the nutrient, which is around the medium. So it's very similar system. We see that happening in experiments. So the tumor is growing, it's all fine, and eventually the cells in the middle start to die out. We see again, because the tumor absorbs nutrients, we have a typical diffusion length that I am giving you the relation again. The diffusion length is the square root of diffusion over decay constant. So as you go closer and closer to the center, you experience less and less oxygen concentration. And the cells change state. If they are consuming a lot of fields, a lot of they're experiencing a high concentration of these nutrients, they are proliferating. If it's not so much, they go quiescent. And if it's under a threshold, they go necrotic and they die. And that's what creates the layered avascular tumor spheroid. We are also going to discuss what are the appropriate boundary conditions. We're going to choose one of them. We will go with medium holds the nutrient at a constant value. But the code itself, we are going to build on the next lecture. So for now, please answer the questionnaire.